Hi there, welcome to your lesson on applied quadratics. Here's an application of quadratic models. We have Dwayne "The Rock" Johnson jumping off this crane, trying to make it in this window in this skyscraper. I think in the movie he makes it, but clearly here we can see there's no parabola that can model a jump that will make it into that window there. Anyway, quadratic models, very important. You may find yourself in this kind of situation someday, and you need to definitely plan out your parabolic jump path appropriately. So let's begin here. We have area and quadratics forever connected. So here is a square. Let's say that square has sides 6 by 6. Well, we know the area will be 6 times 6, which is 6 squared. So we already see that square popping up there, right? 6 squared. What if we have another shape? It's a quadrilateral, not a square this time. It has sides of x and another one x plus 6. Well, what will the area be of that one? The area is x times x plus 6, which yields x squared plus 6x. So notice we have the x squared again. That is why I said quadratics and area are always connected. So we always begin our quadratic word problems or applied problems with area problems, because for many centuries anything to do with unknown dimensions and finding the area has always led to a quadratic, and that's one of the big foundations of quadratic models. So let's begin with a problem like that. We have a rectangle. It has a perimeter of 70 meters and an area of 264 meters squared. Find the length and the width of this rectangle. These problems always begin in the same way. We have two sets of information. One is about perimeter, one is about area. So that gives you a clue right in the beginning that we might have two equations to help us. So here's a rectangle, and we know the dimensions are going to be some length x, some length y. We don't know what they are. We know the perimeter is 70, so 2x plus 2y is 70, because the perimeter will be the sum of all those sides. That's one equation. We also know the area is 264, so let's write the other equation. X times y equals 264, because that times that gives you the area. Now we have two equations. Each of them has two variables, therefore it cannot be solved. But two equations have the same two variables, so we can combine the equations to solve. So for example here, I can divide everything by 2 to get this. Then I can rearrange this to solve for x or y. I've decided to solve for x, and I get 35 minus y. So that can now replace this x in the area formula. So that x has been replaced by 35 minus y like we got here. Now we have an equation for area that doesn't have two variables anymore. It has only one variable, y, and that allows us to solve things. So if you continue on solving this quadratic, you can find the length and width of the rectangle. So go ahead and solve for y there. What do you get? Okay, multiply those out, you get this. Move everything to one side, you get an equation that looks like this. It's a quadratic. Again, it's an area problem, therefore we have one dimension times another. We have a squared value. So we have our quadratic that represents the area. And now we can solve this. When you solve that, it can factor y minus 11, y minus 24. That means our two answers for y are 11 and 24. So this length here, because that's what y represents, can be either 11 or 24. So if y is 11, then we can put it back in this x equation. If y is 11, 35 minus 11 gives us 24 for x. Or if y is 24, if this was 24, then we put 24 in here and get 11. So notice they're just the reverse values. Basically, it's saying in the original problem, when you set up x times y as our area, it's unclear which is the longer one or the shorter one. So basically, when we get an answer, it produces both the longer and shorter option. All right, simple problem, important substitution to know here. Let's try another one like that. So try this one out. We have a farmer who wishes to enclose, that means put a fence around a rectangular garden with 100 meters of fencing. Same kind of problem. We have a certain amount of fencing. In other words, we have a perimeter. So find the length and the area of the garden in terms of x. Then find the width of the garden if it has an area of 525. And finally, find the maximum. So let's begin with A and B. Okay, for A and B, check your work. Here's the rectangle. We have a length like this, given in terms of x, it said. All right, so that's what it is. Then you have your area formula when you multiply these two dimensions. Then you set it equal to 525. You're trying to find an area of 525. multiply, create your quadratic, factor, and solve. You have two solutions. So x can be either 15 or 35 in this case. So what's the maximum area this garden can have? Well, whenever you think maximum or minimum, you should be thinking the vertex of a parabola. So what is the vertex of the area parabola? So here's our area parabola right here. Not this one. It's this one, right? Because this one is when the area is 525. But this is the general area formula, where you can find any area depending on x. So what's the vertex of that one? Okay, so we use negative b over 2a. If this was multiplied out, it would become this here, 50x minus x squared, right? So negative b is negative 50 over 2 times negative 1, which is 50 over 2, 25. And then put that into the area formula, and you get 625. So if that 25 goes back into this formula here, we get an area of 625. And we can see that on the graph as well. If we took this area formula here and graphed it with a here being y equals this equation, we get this parabola. And we can see the maximum point is here. And since y represents the area, we can see the maximum area is right here at 625. And there's no area here, but maximum is right there. So we found the max area. Okay, try the same thing, this problem here. Solve the steps step by step, and in the end, again, we're trying to find the maximum possible area. And also, what are the dimensions? If it had an area of 800, what would the dimensions be? And then, what would be the maximum possible area? Okay, check your work for this one, right here. So, there's the rectangle, there's the area formula, solving it with an area of 800, and getting these dimensions. So x can be 20 or 40, and that means that that each of these sides can be either 20 or 40. So there's the dimensions. And then the maximum possible area, check your work here. Again, there's our area formula. Here's simplified like that in standard form. Finding the x value for the vertex, putting it in, finding the y value. So we found out the maximum possible area is 900. So when we solved question B, that was only one possible area. But the maximum area is 900, and that occurs when the sides are each 30 by 30. So it occurs when it's a square. All right. When it was a 20 by 40 rectangle, we had an area of 800, but the maximum area occurred when this is actually a 30 by 30 square. All right, try this one here. Okay, this one's a little different. We have an original rectangle like this. Then we're told that the length is decreased by x and the width is increased by x. So here's 16 plus x, and here's this one decreased by x. So now we have this new rectangle, which has this area, 378. So that new rectangle, that area, that side multiplied by that side equals the area. Change this into a quadratic, move the 378 over to get 0, then it can factor, and we get two answers. X is 2 or x is 5. All right, so that means that the dimensions of the rectangle are 18 by 21, because if x is 2, then we have 18 here and 21 here. And if x is 5, we have 21 and 18. So again, 21 by 18 for both situations. Dimensions just mean the length and width. Okay, try this one. Okay, try this one out. We're looking for x here. This is a right triangle, so you might use a famous theorem. Okay, let's check our work. Hopefully you're thinking Pythagorean theorem. This side squared plus this side squared equals the hypotenuse squared. So there's that side squared plus that side squared equals that. There's a lot of expanding that has to be done here. Check your work carefully. Expanded, expanded, expanded. Combine everything, move it all to one side, and you should end up with this quadratic. Solve that quadratic, simplify, divide by 6, factor x times x minus 10. So our two solutions are x equals 0 or x equals 10. 0 won't work as a length here, but 10 will work. So now we know this triangle can have sides of 30, 16, and 34. Okay, let's try another one. So another common applied problem in quadratics is when we have a height formula, because when we throw things on planet Earth, they follow a parabolic path through the air because of gravity. So we often have these height equations which have a parabolic shape. So height based on time, all right? So the height of something based on the time it was in the air. So this is a ball that was thrown, and The time is in seconds, h is in meters, the height. How long was the ball in the air for? Think about that. If you have a parabola, imagine this parabola. First of all, if a ball is thrown, the parabola should be like this, concave down. And we can confirm that here by seeing an a value that is negative. Okay, if you're looking for the time the ball's in the air, let's look at it this way. So we're going to find the x-intercepts to find the starting spot and the landing spot. So here's our function. We can use either the Poly Simulation 2 app on our calculator, or we can use quadratic formula, because this doesn't factor. And we should get two x-intercepts, or in this case, the t-intercepts. So there's our two t values. Notice one is negative. Obviously, we cannot go back in time, so we know the ball started at time 0, and then it hit the ground at this time. So the ball was in the air for 2.993 seconds. All right. Looking at the parabola for that, looks like this. So here's, we can see our c values 2, and that's our y-intercept. So it means the ball started at a height of 2. It was thrown, it went up, came down 2.993 seconds later. There's that negative t value. So if you took that 0 here is when the ball started its motion, but if you went back in time and went to here, it would be on the ground in negative time. That's all that's showing. But basically our flight time is this 2.993. Okay, try another one like that. Now let's check our work. So here's the parabola for that. We can see maximum height is here. And then it says, for what length of time will the ball be higher than 20? So we set the equation equal to 20. We're saying if you drew a line y equals 20 across there, you would have when the ball is above that line. So I should add that line here. So now I've added the line y equals 20, and we can see there that's when the ball is above that height. Therefore, if you knew this time and this time, you could find out the amount of time it's in the air there. So you find the intersections of the parabola in that line by setting the parabola equal to that line right here. Create a quadratic, solve it. When you solve that quadratic, you get 0.99 and 3.905. So that tells you right here 0.99 and 3.905 here. So if you subtract those, you find out it's 2.912 seconds between those times. Study that carefully. That's an important kind of problem. Okay, let's look at another one. Try this one. Okay, same kind of problem. It's good to practice these a few times to make sure you got it. Check your work here carefully and pause if you need to. I'm going to continue now. Okay, here's another problem, very different. See if you can read it, set it up, and solve it. How many citizens were there on this trip? Take a look at the work. So the cost of the bus is the number of seniors times the price per person. So before, we knew the bus cost 160, so some number of seniors each paying a certain price gives you the 160 total. However, after we had 160, they're still paying 160, but the seniors, the number of seniors decreased by 8, and the price that each one paid increased by 1. So here's our new equation. This one, if you take a look at it, has S and P in it. So here we're going to solve for S here, or P. You could have done P also. And I got this equation. Now I'm going to take that, substitute that in for S here. And then we have this big quadratic. This quadratic takes a little work to solve. I multiplied these out to get this. I see 160 on both sides. I can cancel to get this. I see a p in the bottom of the fraction, so I multiply everything by p to get this quadratic. Now I see 8, 8, and this can be divided by 8, so I divide by -8 everywhere to get this. Factor, solve, I find out the number of people is 4. So if there's the price per person is 4. That means there was 40 seniors to begin, because that makes 160 in total, 4 times 40. Great problem, a little bit different. Study it carefully. Let's finish with this one, also a little different. Take a moment to read the situation and then try question A. Okay, in A, we need to figure out the price. The price is now 12, the original price, plus 50 cents for every raising of the price. And there's X raises of price. So there's that expression. Let's try B. Okay, number of apple pies. It was 40 sold originally, but it says there's one less pie for every increase in price. So minus X. For example, if there's 5 increases in price, it would be minus 5. Okay, try C. Write a revenue model. Revenue, remember, is how much money you make. Okay, and checking our work. So the revenue is the price you charge right here times the number of pies you sell. Finally, in D, find the maximum revenue you can get. And what would be the price that gives you that maximum revenue? Okay, so hopefully you found the max point, the vertex, and you see it's 8,512. 8 being the number of X raises in price, so that means your price will be 16.